Hi, my name is Joseph St. Peter, and I work at the Center for Spatial Ecology and Restoration at Florida A&M University. Um, and I'm going to present about a recent project we did, spatially quantifying forest damage from Hurricane Laura. So I think there are questions that you can put into the chat right there, and I can address those as I see them. So feel free to type those in. All right. Now I have to figure out how to go forward. Okay. So, Hurricane Laura forest damage project. This was a Hurricane Laura was a Category 4 hurricane that just made landfall on August 27th. It was over in Louisiana. And one of the things that came out of this was that there was a definite need for remotely sensed damage assessment at the spatial extent of the damage. So as the hurricane comes in, it creates a huge swath of forest damage, specifically is what we're talking about here. So it covers a large area. So we wanted to give them something to cover the extent of that landscape extent damage. And then, but it also needed to have a high spatial resolution, so at least a medium resolution, so managers could actually use that on the ground at the stand level to direct their restoration efforts. And it needs to be done rapidly. So one of the things that is interesting about when these hurricane damage occurs in the Gulf and other areas is for the foresters, so national foresters on the ground, they need to turn around and report within weeks. And these are the same foresters that live in that area and land managers who live in that area. So they might take days just to get out of their driveway because they suffer damage as well. So and then they have to turn around and quickly give this report up to Congress. Uh, so they're definitely in a position where they could use some remotely sensed help. And while there is some work that has already been done in that area, there's still this need for a really high spatial resolution and forest specific damage. A lot of the damage, is understandably looking at human damage, infrastructure damage. But as far as forest damage, a lot of it is still done by flying helicopters, flying airplanes, and looking out and drawing on a map. So previously, we'd done this work on Hurricane Michael that occurred in Tallahassee, just west of us in 2018. And so for this talk, I kind of want to do a little bit of give you an idea of art of the possible. I'm sure I have a lot of GIS savvy folks here, and this is just demonstrating how you can use GIS as a data science tool, as well as a lot of the out-of-the-box, mapping features that we use it for. It can also be your primary data science toolbox, and that's what I want to demonstrate here as well. So overview. So the project, we use Sentinel-2 imagery, which is a 10-meter imagery product. What was it? All right. And for our plots, we use these FAA plots to do basal area mapping. So the basal area, I'll explain really quickly. Basal area is a common forest metric. So in case you don't know, imagine all the trees in an area, say an acre, and if you cut them all off and you look down from above, how much volume those stumps would take up in the area. That's what basal area is measuring. Okay, and so we created this general linear model of basal area. And that just gives us the pre-hurricane, how much basal area was out there before the hurricane, and then how much basal area was out there after the hurricane. You subtract the two, and there you go. There's your damage. And I also had a classification model, and that was going to help us direct our efforts just to the forest and not to the non-forested areas. Okay, so this is our study area. That's Louisiana and Mississippi. So this is where Hurricane Laura impacted. You can see on the right there, there's our wind speed bands, our nice little hurricane graphic. And you see the force of the winds were quite significant. And then up here on the right, when I zoomed in, is these are our sentinel tiles that is our study area. So there's 9 sentinel tiles. So sentinel imagery comes in these tile formats. They chop it up so you can go scene by scene, tile by tile. And so these are the 9s that cover the largest forest damage areas. And then these black outlines, those are our federally managed forests or lands in the area. So those are really what we were concentrating on. Those are the people that we were giving this information to. So you see those are concentrated in these 4 up here. All right, so now we're all oriented. So like I said, we previously done work in this area on Hurricane Michael. I'll wait till everybody gets up. And this is that map, the result of that work. You can see here's the track of Hurricane Michael. Here we are. I don't know if you guys can see. If this was a non-virtual, I'd have a laser pointer and I'd point at stuff. So maybe you can see my cursor, maybe you can't. But the black outline is the Apalachicola National Forest. And so west of there was the major impacts of Hurricane Michael. And so the red is where there's a lot of forest loss. And the blue is where there either wasn't forest at all to begin with or wasn't forest loss. All right. So again, that was a basal area damage map that we produced after Hurricane Michael. It used the Sentinel-2 bands, those 10-meter bands, and spectrally normalized imagery, which I'll get into a little bit more because it's very important when you try to do this modeling work to get everything, all your data on the same range. And then we use 2 phenological periods of imagery data in this analysis, the winter and the growing season. And we had first and second order texture. First and second order texture measurements, those are one of our independent variables. It's just a fancy way of saying standard deviation and gray level co-occurrence matrix, which is already a fancy term. But I'll get into it in a little bit. So when this occurred, Hurricane Michael occurred, we had already put out all these what we called restore plots, these 231 forest plots. Our work wasn't hurricane damage work, it was forest inventory work and restoration. We have this restore project and Tate's Help project where we're trying to restore the forest to help the bay, which actually Christy Crandall has a talk later today at SHRUG that she goes into that in detail, which is really good. You guys should check it out. So we already had all these plots out there and we were already doing our inventory, getting an idea of where the trees were, how much of them were. And then the hurricane comes in and knocks everything down. And so now we're back to square one. We're like, okay, we have to go out and figure out what kind of damage that this had on our area. So that was part of the impetus behind doing this. But luckily, because we already had those plots out there, we could use the data from those plots to train our model to give us the pre-hurricane basal area, and then use that same model and apply it to the post. And like I said, it's pretty easy. You got your pre, you got your post, you subtract the 2, and that's your damage. We also use this hurdle model approach. We had this softmax neural net pine presence model, and that's we just wanted to base our model off of areas where there were trees and not zero inflate it, which means we were just trying to make a more accurate model. And we actually had a pretty good model of base area R² value, about 0.5. And so that worked really well. And then we also did some masking on the other end where we had some burned areas and non-forested areas. So mostly what we've done has been an ArcMap. Nope, we're moving to ArcPro, and actually we're moving to cloud-based services in Python. But we had this roster utility bar, use this ArcMap add-in that our friends over at the Rocky Mountain Research Station, John Hogan specifically, has developed over the last 7 years. And it turns, like I said before, it turns your GIS into much more of a data science tool. It is poorly named. It's not just the RAS utility, it's vectors and data and other data as well. They said it's an Esri add-in toolbar. And it focused on reducing processing time and storage using function modeling and some really cool concepts, some of which are actually integrated into ArcPro now, which is good to see. But all this massive tool set of statistical tools to help with data acquisition, sampling design is not It's not really reproduced yet in the out-of-the-box arc, so we're still using this and developing our coding library in Python as well. And it gives us a lot of data acquisition tools, sample design tools, sampling, raster analysis, and a lot of statistical modeling, machine learning. So there's a lot of regression, logistic regression, softmax neural net. We just use the two. We just use the general linear model and the softmax neural net model. Those are just supervised classifications. I'm sure the GIS professionals here have done a lot of classification, so it won't be unfamiliar to you guys. If you haven't, it's okay. All right, so the overview of this project. So like I said, we're estimating and mapping the base area before and after Hurricane Laura, and we're trying to do it rapidly. We ended up being able to do it within weeks of the hurricane and get that information out to the land managers. So that was good. And categorize, that's kind of a preview. That was the results. So we categorized and mapped these hurricane damage, again, based on the before and after base layer estimates, using the classification models to define the forest areas. And so this supervised classification, this is the little formula I had, very simple. Base layer on one side, a function of your imagery variables, and FA plots on the other side. I always try to keep that in mind. It's relatively straightforward. We're trying to predict base layer based on what we see in the image and what we have on the ground. Try to keep that in mind because it gets complicated fast. As this flowchart will demonstrate, this is my attempt at showing what our project looks like in a flowchart. So I'll walk through it really quickly. So we start with the Sentinel-2 imagery. In case you're not aware what Sentinel-2 is, it is the European Space Agency satellite. Sentinel-2 is specifically the multi-band, multispectral imagery. All right, and then we select it. So they have every 3 to 5 days, they get imagery. And when I say image selection here, it's to select for non-cloudy days, and also days that are close to when the hurricane occurred. For the pre-hurricane stuff, I actually went with 2018 data because the pre-hurricane is just trying to give us a baseline, a good starting point. So I just was trying to find almost the same day of the year. So again, it happened in August. So I found an August data set with less cloudy days, and then also that was close to when our FAA points were sampled. I'll go into this a little bit more later. And then as far as the post-hurricane image, I was just going to use anything they got because we wanted to get as soon as we could. As soon as that satellite passed and gave us data, we wanted to use it. All right, so to set up the models, we used this pre-hurricane. We created these independent variables or features, if you're in a data science term, which started with the normalized imagery. I'll go into the normalization process pretty soon. So, but that's your imagery, your basic, what the pixel value is at your plots. And then these are the two texture measures I talked about, the first order standard deviation and the second order horizontal contrast, GLCM. And those just give you an idea of, so you have a pixel value, and this is how that value in the neighborhood. So that's the texture, the pixels in the neighborhood of the pixel you're looking at, how those vary. And then we got our field plot data to inform the model. So that's our dependent variable, if we want to use the statistical terminology. And that all informs our general linear model. So we're just nothing fancy there. It's a general linear model with multiple variables input. And that gave us our basal area estimate. And then we applied the same model to our post and subtracted the pre from the post. And then we had this classification model down here, which gave us some masks to mask the data to just the areas we're looking at. So we had a forest and a cloud mask. Categorize those basal area estimates that would go from 0 to 250 into light, medium, or heavy or severe damage, and then we mapped it. So that's everything I did here, and I'll go into details about what that is. I'm gonna start with the spectral normalization, because this is, if you've done a lot of work with imagery, one of the things you realize is if you go beyond the tiles, the Sentinel tiles that I showed, or you go multiple days, you have to deal with the images are are not lit the same. You know, the sun moves, the the image changes over time. So what you think of as red in one image is not necessarily red in the other. You know, it could be 200 here, it could be 210 there. I don't know if I'm explaining that perfectly, but the idea is you got to normalize, get all of this imagery data, all these values contained in these pixels onto the same range, onto the same spectral range. So we call it spectral normalization. There's a lot of ways to do this out there. People who do work with imagery probably not unfamiliar with this. It's important because when you start modeling across these areas, your model is going to be trend to the global mean. It's not going to be as accurate if you don't deal with normalization of the images. So that's what we did. We have, based on a lot of previous work, we have the aggregate no change regression spectral normalization. And I'll explain what that is, but here's what it looks like. This is a Hurricane Michael project. Here's the before, where the raw images from Sentinel-2, you can see there's a big difference between these two. And then here's what it looks like afterwards. You couldn't even tell that there's a line there, and these came from different months and actually different years, these images. And so here's kind of a general graphic, what that entails. So I'll start with over here, actually, these two grids. So the aggregate part of the aggregate no change regression is to deal with the co-registration errors. So a lot of GIS folks out there probably are aware of registration, where this pixel on the ground is, you know, at this point. And when you're trying to assign the next image that goes over there, saying it's the exact same point as well, but there might be a little a shift. So that's what this red circle is highlighting. And for Sentinel-2 imagery, they've improved it recently, but when I made this graphic a couple months ago, their temporal registration error was about 12 meters in their 95% confidence interval. And their absolute was 11 to 16 meters. And when you're looking at a 10-meter cell, that means you might be shifted over an entire cell and then some. So what that means when you're looking at change detection is if you're in an area that is heterogeneous, so a landscape that changes, this will inflate the amount of change you got. So you got to deal with that, especially when you're doing spectral normalization, because you're trying to put everything on this line over here and saying from your reference image value, I have this point and it's red, it looks like this, and then this one is there. So you're trying to graph it there, and then you shift your target image values based on this relationship to get them close to the reference image value. So what we did to deal with this registration error is we aggregated it up. We're not looking at a pixel to a pixel, we're looking at a 50 pixel square to a 50 pixel square and using the mean of those values. So that deals with that registration error. And the no change part is these outliers here. So say you have a clear cut, a building went up, or you just had a fire and in between those images, then the no change, we just drop those outliers. That's a user set. We set it to like 10, 15, 20% of change based on how we're looking at it. And then we get our value coming out. And again, this is all done using the RMS raster utility. It's just a quick button, click, click, spectral normalization. And this uses the overlap between the two images, that overlapping area. And it's done with each spectral band. Okay, so that's aggregate no change regression. It's really helpful because when we did this project, I could take all the overlap for the tiles from before and after were the entire tile. So I had a lot of data to work with, and I got all of the images, the data on the same spectral range, which means my models, I could build it once in the pre-hurricane and apply it to all of the post-hurricane stuff. I could build my model once and apply it to everything. And this is what that looked like, spectral normalization in our study area for Hurricane Laura. These lines are not, these horizontal lines, I think are just a display issue, but you can see the boxes, the differences here on the raw imagery. This is for the pre-hurricane stuff. And then after we applied it, a lot of that goes away. Oh, and those are the dates of when I got the tiles here, and the different tiles I use. So most of them are from this date, this August date here, but I also got a couple of dates around that, even one from 2017. So that's the pre-hurricane. That's the setup of our model. And so once you have that imagery, we then create these predictive surfaces. These are our independent variables. These are the features that we're going to use to inform our model. And so we start with the Sentinel bands, the 2, 3, 4, and 8 band. Those are all the 10-meter bands. Sentinel-2 has more bands, but they're higher, coarser resolution. And these are the blue, green, red, and near infrared bands. So we use those pixel values by themselves, but we also do, like I said, these texture measures here. In a 3x3 moving window, so 9, we use standard deviation and the horizontal GLCM. And here's a good graphic I got from John Hoagland about explaining what those are. Standard deviation, you're looking at all those 9 cells, and you're just, you're getting the standard deviation. It's relatively straightforward. The gray level co-occurrence matrix, the GLCM, is maybe something a lot of people aren't as familiar with, but this is kind of what that means. So you're looking at the change between these 2 neighboring cells and these 2 neighboring cells in this horizontal way. You can also do, vertical and even diagonal. So in our Rocky Mountain Research Station raster utility toolbar, it's actually a true GLCM. There's not binning. A lot of programs will bin them because it is pretty complicated, but our friend, Dr. John Hoagland, was brilliant enough to figure out a way to do it without having to bin. And then we have a lot of these variable selection options. So once you do this, you got 4 bands, you have 3 different ways of looking at them, you got 12 variables at that point. And then you can select using a principal component analysis, which is what we did with the Hurricane Michael, or an iterative variable selection, some automatic selection routine, which I've also done before. That's trying to get it parsimony. Or you can throw the kitchen sink at it. That's not a technical term, it's just I used everything. Because in this case, I'm more concerned about getting the model really consistent and good, and not as concerned about getting the basal area as accurate, because I'm looking for the change in the basal area, not so much getting the exact basal area right on, which I usually am. So in this case, we threw the kitchen sink at it. We used all 12. And so those were our independent variables or features. This would be the dependent variables, our plots. We were lucky enough to be able to use FAA plot data because unlike when Hurricane Michael hit and we already had our own plots that were designed to be related to remotely sensed imagery, we don't have plots in Louisiana, but FIA does. FIA is Forest Inventory and Analysis. It's a U.S. Forest Service branch. And these are what their plots look like. They're kind of a turkey foot. These are kind of legacy plots. This was before they related it to remotely sensed imagery. So we're using it for what it's not intended to be used for. But in the past, we have used these plots with remotely sensed imagery. The caveat here is because it's this turkey foot area, your plot is actually 78 by 70 meters. And you're only actually observing these small circles in each of those plots. And that means you're only, of what you're calling a plot, that whole square, that 78 by 70 meter plot, you're actually only observing 12.3%, which is not ideal when you're trying to build a model with using a small subset. But these are meant to be regional scale, so they work fine for what they're intended for, but we're trying to use them differently. So like I said before, when we had Hurricane Michael, we had our plots, which were these 36 by 36 meter plots with these 4 giant circles in it where we actually took observations. And those meant that our observations in what we're calling a plot was 78.5%. And that really helps with our models. It means we can put less plots out there and get better spatial accuracy. So that's the caveat. We were using these ones over here. And so our model results, and skip right to the results of the basal area model. So we were only able to get the FAA plots on the federal lands in the study area, those black shapes that I showed you in the study area. And so that meant we were also restricted to the number of plots we had. We only had 208. And while before, when we had our restore plots, we had 231. It's not a big difference there, but this is kind of a tip for you guys out there in GIS land. When you when we set out our restore plots, we looked at the imagery first and did a quick analysis to decide to capture the range of data we're getting from the imagery, we need to locate the plots in these areas. So GIS and image analysis informed where our plot locations were and our plot design. So if you're in an organization and you guys are putting out plots, go ahead and assert yourself and say like, hey, if you really want to maximize our efforts here, talk to me. I'll help you guys set up those plots areas. So that wasn't done here. So we had a smaller area, a smaller number of FIA plots, and they covered from date ranges from 2015 to 2020, but mostly this is when they went out and actually measured the plots. But they centered around 2018, which is why I chose that August 2018 pre-hurricane imagery. And so we used the kitchen sink, all 12 of these predictive variables, in a 8x7 window. So that covers our plot, the 78 by 70 plot. So related it to those sides, the mean pixel, standard deviation, GLCM. And our general linear model of base area had these stats: our root mean square error of 36 and R squared of 0.23, which was about as half as good as our previous one. This is not great, but it's enough to get on with. And this is just our plots square feet. So this is just the range of basal areas that we had in these plots. So some really small ones, a lot of medium ones, and some very high ones. So now we had our model, but we also had post-hurricane imagery. It was very cloudy. Once a hurricane hits, for quite a while afterwards, there's going to be some clouds. And just in general, we live in a relatively cloudy area next to the coast. So getting cloudless imagery was an issue. But when you're in post-hurricane imagery, you wanted to get going. Again, we wanted to get rapid information out there. So this is just a picture of 3 tiles of Sentinel-2 tiles on September 9th. So this is one of the first returns that wasn't completely covered in clouds, and you get an idea of what we're looking at here. So there is some good data in here, in these gaps between the clouds. So one thing you could do in order to do this analysis is you could wait. You could wait for cloudless images. This specific satellite passes every 3 to 5 days. So you could just wait and wait. But again, we're trying to get stuff out there rapidly. So can we use these cloudy images? So there's a couple ways you could. You could use it in combination, which is what we ended up doing. Or are there Sentinel-1 options? Sentinel-1 is the satellite that has radar. If you can get through the clouds, you can get some data there, and maybe you can build some sort of relationship between the radar data and the multispectral data. We're still looking into this option, but because that's a project on its own, we went with this combination routine. In order to use a combination, so when I say combination, I mean, so you got a cloudy day on September 9th. Maybe you get a cloudy day on September 13th or 15th or 10th, but it's slightly different clouds. The clouds are different spaces. So if you can mask out the clouds, you can put those images together and you can get a pretty good coverage. So that's what we ended up doing. In order to do that, you have to have a decent cloud mask, something that identifies where the clouds are. There's a lot of out-of-the-box options. The ESA, European Space Agency, has their own processing that you could use. But we ended up, or you can do your own. You can classify your own, which is what we did. And I can tell you why we did that. It was because of this bullet point right here. We wanted the accuracy and the flexibility, because we didn't want to just get rid of the clouds. We also wanted to highlight the forested area and not predict on the non-forested area where we didn't have information. And so we had this previous work that we did right down here. This is a land cover classification, a most likely class that we did based on NAPE imagery. So we had done this before. We had our own methods to do it, and it was relatively fast. Again, this is a supervised classification. This is the classification from the flowchart from earlier. So we randomly selected 1,064 points in our images, in our Sentinel images, and I classified them into 6 categories. And these categories are just based on what I could use for, oh my gosh, I'm way behind. This is classified into these 6 categories. All right. So this is the classification model workflow. Again, selected random samples, classified samples. There's our independent variables. And we got these surfaces. All right. So these are, I just want to go over what this looked like on the ground. So this is I'm just highlighting one tile, September 7th. We had a good pass, but it didn't cover a lot of our area. September 10th, we had a pass and it covered a lot of our area, but it was super cloudy. September 15th, I might be moving too fast, but September 15th, we had a different set of clouds. So this is what it looks like combined. That area that's still cloudy, I ran the classification. You got the red areas of the clouds, the forest is green, the non-forest is blue, and everything else, including cloud shadow, is black. All right, so we could use this. And September 10th on the left, September 15th on the right. And I zoomed into the overlap area where we didn't have that September 7th, that cloudless image. And you see the clouds they're still quite a bit cloudy, but they're cloudy in slightly different ways. And so I combined them, I ran that classification, I had some mixed success, it covered a lot of the area. And the most important thing, it allowed for results earlier. After September 15th, that's already a long time, that's already a couple weeks after the hurricane landed, so we wanted to get stuff out. So and this also allowed us to not be limited by those cloudless images. So we ran the model on that, the base area model, subtracted the pre from the post, categorized it into these categories you see at the bottom there, light, medium, heavy, and severe, based on the base area loss. And this is the result on the right. There's still some gaps where the clouds were. Luckily, September 30th, finally I was able to get a cloudless image and ended up looking like that. So it did fill in quite a bit with the cloudless, but we still got a lot of the areas, especially the areas with high, heavy impact and severe impact, did show up with the combination. So the drawback of this is that you had to wait a month for this, and then by that time you might be into the winter season, which the trees would look different, and that'll affect your analysis as well. All right, so this is the final result of the whole area. I zoomed in. On your right, there's the study area. On your left, this is the results in the damage category. These are the federal land areas. And this is the track of the hurricane. So zoom in here, there's the Kisatchie National Forest, and you can see those are our damage categories there. Heavy, you can see a lot of the heavy damage areas, and these map pretty well on what we were seeing on the ground. And that's what this image is here. This is a zoom in, this is from NOAA's drone imagery. Unfortunately, we didn't get a lot of this imagery, it was mostly next to the coast, but I just want to highlight. So this area here, this is where there's a bunch of trees still standing. A little bit worse here, you can see a lot of the trees down in this part. And so how did that look when we mapped it using our model? Well, it looked like that. We covered it pretty well. So there's medium to light here. We had some heavy damage here and here. So it tracked it really well. And just so you know, I didn't use that drone imagery. This is what the model actually saw. So it's pretty amazing what we got out of it, considering this is what they had to work with. All right, this is just some more of those drone images. I'm just trying to highlight we're just doing the forested areas, so you can see it's tracked really well to where the forested areas are. Even these really small slips of forest, it does pick that up and shows that damage. More of those images here, tracked. You can see this big patch here that had some pretty good damage, same here. And even these little pieces of damage, like a couple of trees next to people's house, it does pick that up and it shows where that damage was and it wasn't. So we were really happy with the results just qualitatively. Qualitatively. So we accomplished what we set out for. It was rapid. We got it out in a couple of weeks. We have a lot of recommended improvements. One of the big ones I'm highlighted down is workflow. Like I said, we're moving to cloud computing with Python code because this was all on my own local laptop using, ArcGIS. And it would be good if we prepared a lot of this stuff before landfall. That's something we're working towards. All right, so I ran through that last bit really quickly. Those are my acknowledgements. Now I'll take some questions.
Well, thank you very much, Joseph. Down, you guys will see an option there to type in some questions. And looks like we got some coming in. So let's take a look. Tony Cooper, how many FAMU students were involved in this project?
One, me. I'm I'm a FAMU grad student. We do have a lot of other projects that we have a lot of undergrads working on, but we're still, yeah, but because this is such a rapid and relatively advanced thing, I just did it.
That's fantastic. Let's see here. Just rolling through here. Well, Joseph, there was anything else you wanted to add that I know you sort of toward the end there, you had to move a little faster. Was there something you wanted to quickly add?
Well, yeah, I just
We have
wanted
a few
to.
more minutes.
Sure. Well, I'll just say thank you all for coming. I know this is a bit odd having it virtual, but that's the world we live in now. And I just really appreciate everybody's time. This is kind of a start. This is a project we did relatively on the fly. But that's, when we've had so many hurricanes lately that we knew that this is something that needs to be done a lot more, and we need to really get the workflow down in the future. So this is the start of it, but I also wanted to note that for all the GIS professionals out there, this is not necessarily that complicated stuff. So you could do similar work. One of the things that was really helpful in my career is just realizing the power of these tools that we have now, and that if you can think of something, you can do it. So kind of a rah-rah message there. Yeah, that's all I had.
All right. Well, I found this to be very informative, very interesting, and I'm quite impressed. You've done some really nice work, and I'm sure our attendees would agree. We've got a couple of more minutes if anybody has another question. Joseph?
Oh, you know what? While they don't, that RMS raster utility that I talked about, even though it's kind of depreciated at this point, we're moving past it. If anybody is still working in ArcMap and wants one of those data science tools, we also have a bunch of tutorials that me and John Hoagland had put together in the past when I worked over at the RMS. Those can be found. You just Google RMS raster utility. So if you're interested in that kind of the tool, the little add-in that we use, you can go there, and there's lots of ways to learn it.
And Joseph, if anybody wanted to reach you, do you have an email address you want to share out?
Oh, right. That's something I forgot to put on there.
Well, you go ahead. Well, these are being recorded, so if you wanted to just,
Yeah, it's just my name, Joseph.stpeter, Joseph.stpeter@famu.edu. Yeah.
Excellent. Well, thank you so much, Joseph. Really appreciate it. The next session is going to start at 10:45. We've got a short break before that. I want to thank Joseph, a virtual clap. You have lots of people clapping for you. We appreciate it. And thank you for participating.
All right. Thank you all.
Thanks, everybody.